Hi everyone, in this lecture we are going to talk about pigeonhole principle, which again it's a very simple principle, but sometimes it's very useful in solving competitive programming questions. So let's talk about pigeonhole principle. So it is based upon a very simple idea, and let's start with an example. Suppose we are given 5 pigeons and there are 4 pigeonholes, okay? And you start putting pigeons one by one into each pigeonhole. So what is going to happen? So if you have 5 pigeons and you only have 4 holes, then if you put this pigeon here, 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 then if you want to put this pigeon, then this might one of the hole will contain at least 2 pigeons. Okay, so this is what is going to happen, and you can see it is as obvious it is. So then you will have one pigeon left and you can put it into any one of the pigeonholes. That means, to conclude, when the number of pigeons is greater than the number of pigeonholes, then there will be at least one pigeonhole with at least 2 pigeons. Okay, so that's the whole idea of pigeonhole principle. And now you may ask, why do we need this? This is something that is very obvious, but yes, we will be using this simple concept to solve some interesting questions. Let me give you another example, hair counting example. Let's say the amount of hair is expressed in terms of number of hair strands. The average human head has about 1,50,000 strands of hair. Assuming no human has more than 1 million strands of hair, that is 10 lakh. Given the population of a city is, let's say, 30 million, okay, then definitely we can conclude that there would be many people who would have exactly the same number of hair on their head. Okay, so very simple, we are saying, okay, 1 million, so anyone can have hair in the range 0 to 1 million on their head. Okay, but if the number of people who are there in a city, they are in the range, let's say there are 30 million. Okay, so there are 30 million people, so each of these 30 million people needs to be clubbed into these buckets. So this is basically buckets. Okay, we can say definitely a lot of people are going to have overlap and there would be many people who would have the same number of hair on their head. Okay, so this is another way of you can say it's just what it's pigeonhole principle. Okay, so we are putting people into buckets where each bucket denotes the amount of hair on their head. Okay, and that's all for this small introduction, and in the next lecture we will start solving problems on pigeonhole principle. Hi everyone, in this lecture we are going to solve a problem. The name of the problem is divisible subset, and we are given a multiset of n integers. So multiset is nothing but a set which can contain repeating elements as well. Okay, and we need to find a non-empty subset of it such that sum of the subset's elements is divisible by n. So this n is nothing but the size of the subset. So given a set, we need to find a subset whose sum of elements is divisible by the size of the set. Okay, so n is size of the actual set. Okay, so we are not given a different number, it is same as the size of the original set. And if such a subset does not exist, we will print -1. But if it exists, what we are going to do, we are going to output two lines. One is the size of the subset on the first line. Okay, we need to tell what is the size of that particular subset, and second is we need to output the list of indices that form the required subset. Okay, and you can see n is very large. So actually this question is from the platform CodeChef. I will just show it to you. So you can see this is from CodeChef. The problem is div subs, and again we have already gone through the problem statement, but if you look at the constraints here, so we are given each element of the multiset is a positive integer not exceeding 10 power 9. Okay, which is fine. And now we are given three different values for constraints. So if you solve this problem for n up to 15, okay, you get 37 points. If you solve it up to n equal to 1000, you get 37 plus 24 points. And if you also solve for a larger value of n, that is 10 power 5, you get 39 more points. Okay, that means there must be multiple approaches to solve this particular question. Okay, now let me also give you an example. So if you look at the input, the first line of the input contains an integer t denoting the number of test cases. Okay, then followed by the n and followed by n integers. All right, so we have one test case which contains three integers, and the integers are 4, 6, 10. So these are the values in the set, and now we need to output, okay, any one set, output any one set such that sum of the integers in that particular subset, okay, is divisible by 3. So in this case they are saying, okay, I will just pick the second element, that is 6, and 6 modulus 3, that is equal to 0, which is fine. So that's why you can see the output is what? The output is the set size of the set is 1 and the element index is 2. This is what is the size. So we can pick as a subset, the sum is 6 and it is divisible by 3. Okay, so the only thing is it should be non-empty. That means at least the size should be at least 1. Now we need to see what can we do. Okay, so what is the brute force way of generating all possible subsets? So if you're given an array of size n which contains some elements a, b, c, d and so on, so for each element you have two choices: either you include in the set or you do not include it. Okay, so if the array is of the size n, then you can generate 2 raised to the power n subsets. Okay, and if n is large, this is going to be a very huge number, and it's obviously going to give you the time limit exceeded error. So for n, the value of n up to 15, you can easily do work of 2 raised to the power 15, and you can definitely use the brute force approach. This will work fine here. So generate all subsets and print any one subset that follows this particular property. But for n that is equal to 1000, okay, that is equal to 1000, we might not be able to do the same. Okay, we cannot do 2 raised to the power 1000. This is going to be huge number and it's going to give you TLE. Okay, so this exponential complexity will work only till 20 or 30 at max, because 2 raised to the power 20, this is of the order 10 power 6. 2 raised to the power 30, it is of the order 10 power 9. So even this is not going to work. Okay, so for larger values greater than 20, it's going to become very slow. So now what do we do for n equal to 1000? So one thing we need to recall is there are generally two terms. One is called a subarray, okay, and one is called a subset. And all subarrays are also subsets of okay, so subarrays are also subsets. So I need to find only one subset. So if I can ensure if there is one subarray, then we have also found out a subset. Okay, then we have also found out a subset. So ensuring a subarray will ensure a subset also exists. So now let's see if we can how many subarrays we can have for an array of size n. So subarray is a continuous part, and a subset might not be continuous as well. Okay, so let's see if we have an array like this, then a subarray is a continuous part of the array. Let's just starting from this index I ending at till this index j. Let's say this part of the subarray we have, and somehow if we are able to prove that okay, there would be this subarray which will have which will follow this property that sum of elements from ai till aj, sorry, ai plus 1 till aj, the mod of this would be divisible by n, then we do not need to look for subsets additionally. Okay, if we can find a subarray, then subset is all subarray is also a subset. So how many subsets you can have? So if n is of the order 10 power 3, then you can pick the starting and ending point of a subset in NC two ways. So roughly we can have n square subsets. Okay, that means for any that is 10 power 3, we can have roughly 10 power 6 subsets. We can find the sum, okay, by generating a cumulative sum array, and we can find the sum. Okay, we know the sum till this particular point, we need the sum till this particular point, and we can find the sum in just constant time. Okay, that means in order of n square complexity, we can check uh, for all subarrays. Okay, but the question is, what if we don't find a subarray? Okay, but now what I'm going to do is I'm just going to jump to this particular part, and I'm going to prove, we are going to prove for this problem a subarray that follows this property, that follows this property that is mentioned in the question, that sum of elements should be divisible by the size of the original array. Okay, will always exist, will always exist. So it's little tricky to think of this, but we will try to prove it using the pigeonhole principle. So now we'll solve for n, that is 10 power 5, and that will also cover the case. We will not need to find all the subarrays. We will just prove that this subarray will always exist, and in the output we only need to print one subset, and a subarray is also a subset. So let's go into what we need to do for 10 power 5 in the next video, and that will give us an idea how we can use the pigeonhole principle. Hi, so let us continue our discussion on the problem diff subs, and let's try to prove that this problem can be solved using pigeonhole principle, and that too in almost linear time. Okay, so we are going to look at how we can solve this problem. So this test case we have already seen, and let's take an example. Let's take a array, let's say 1 2 3 5, and let's say 7. Let's say we have 5 elements in this array, and we need to find a subset, or not a subset, there can be a lot of subsets. So we said we will first try to find a subarray, and we will prove, the claim was that such a subarray will always exist. So we are claiming a subarray will always exist. Okay, will always exist, and we are not going to prove our claim. So what we are going to do, so if you need to find the sum of elements of a subarray, then what we generally do is we make a array of a cumulative sum. Okay, let's make another array, and what we'll do, we'll say, okay, let's find out the sum till this particular point. So this is 1. What is the sum up to the index 0 1 2 3 4? The sum till this point is 3. This is 3 plus 3 is 6. This is what? This is 11, and this is what? This is 11 plus 7 18. Okay, sorry, this should be, yeah, so this sum should be what? This sum should be 18. Okay, so now what we can do is we can say, suppose what we are saying is, we are saying, okay, we'll find a subarray. Maybe let's say this is the subarray whose sum is divisible by n. Let's say the value of n is 5. Okay, so we are saying we know the sum till this particular point is, let's say, this sum b. The sum till before index 1 is still up to this particular point, that is a. So the sum of a subarray, the subarray sum, can be computed in order 1 time, that is nothing but b minus a. Okay, so we are saying b minus a taking mod with n. Okay, that is the subarray sum, and this should be equal to 0. That means B mod n should be equal to A mod n. Okay, so effectively what are B and A? So B and A denote the cumulative sum. So what we do in this particular array is we can reduce everything by mod n. Okay, so if you do a mod n here, what you're going to get? You're going to get these numbers. Okay, so you're going to get 1 mod 5, that is 1, 3 mod 5, 3, 6 mod 5, again 1, 11 mod 5, again 1, 18 mod 5, that is 3. All right, so we are getting so many numbers. So now we also know that something mod 5 will always lie in 5 buckets. Okay, so something mod 5 or something mod n will always lie in the buckets 0, 1, 2, 3 and 4. Okay, so right now what we are getting is we are getting 3 numbers which are getting mapped with the bucket 1. Okay, we are getting 2 numbers which are getting mapped with the bucket 3, and we are getting 0 numbers mapped with bucket 2, and 0 numbers mapped with getting bucket 4, and 0 numbers mapped with getting mapped with bucket 0. So right now this is how the distribution is. But now let me just tell you, there can be two possibilities. Okay, so in the worst case you might get something mod n as 0, 1, 2, 3 and 4. Okay, so we have 5 numbers, and let us assume that these 5 numbers give these 3 different mods. Okay, so now what may happen is, let's say if something mod, if I say okay, the cumulative sum till this particular point is, let's say, 0, then what it means, you already got the subarray, okay, if you have something like if you get this sum b as 0, that means instead of 5 this number would have been 4. Okay, let's take example of this array, that 1, 2, 3, 4 and 7. Then you have got the sum 1, 3, 6, 10 and 17. Then if you do mod with n, you would get 1, 3, 1, 0, and again this is nothing but 2. So if this sum is 0, that means the sum till this particular point, this sum is what? This is a subarray whose sum is divisible by n. So if you get a number 0, then it means you are already done. But suppose instead of getting 0, you get something else. Okay, instead of getting 0, if you get something else as your sum, that number could be 1, that number could be 2, that number could be 3, or that number could be 4. That means it would always lie in the range 1 to 4. Okay, that means it would always lie in the range 1 to 4. Let us say this number is nothing but 2. So maybe what you get is, you get 1, 2, 2 and 3, 4. Let's say 2 numbers, they lie in the same bucket. So effectively what I'm saying is, if you get 0, you already found out one subarray. But if you don't get 0, then what happens? For these numbers you have 5 numbers, okay, and you have only 4 options. You have only four options. That means 4 buckets. That means there would be at least one bucket which is storing 2 numbers which are same. Okay, in this case there are multiple such buckets. There is a bucket of 1, there is a bucket of 3. There are only 4 options for 5 numbers. So according to Pigeonhole Principle, we can say at least one bucket, or at least one bucket, or at least 2 sums will always lie in the same bucket. Okay, that means we found out the values of b and a. So that means such b and a will always exist because of the Pigeonhole Principle. Why? let us look at this example now. So we are saying, okay, this one and this one are same. So effectively, if you pick the entire subarray in this range, that means if you pick these three elements, that is the elements 2, 3, 5, they follow this property. Okay, or if you pick anything in the range, so this one and this one are also same. Okay, that means if you subtract the sum till this particular point is 1, the sum till this particular point is also 1. That means if you subtract this b minus this a, you can again get something like this. So you can get 2, 3. So 2 plus 3, this is also a subarray that satisfies the given property. So here we are saying the sum till this particular point is 3, the sum till this particular point is 3. So if you subtract 3 minus 3, it is also 0. That means these three elements, they will also satisfy the property 3 plus 5 plus 7. So you can see this is nothing but 15, this is nothing but 5, this is nothing but 10. So all of them are divisible by 0. All of them are divisible by 0. So effectively, in the cumulative sum array, what should happen is either one of the values would be at least 0, or if it is not, if none of the numbers is 0, then we are saying at least two numbers will have the same value, and the area of the array in between these two indices will form your subarray, whose sum mod n would be 0. Okay, that's the whole idea. So I hope you understood how we have applied pigeonhole principle in this question. Okay, so if it is still not clear, so we are saying pick any two numbers which are same. So we are saying, okay, we'll pick the numbers till this particular point, let's say this one and maybe this one. Okay, if I subtract these two, okay, if I subtract these two, so that effectively means I'm taking all the elements of the array till this particular point, summing them up, and I'm subtracting all the elements of the array till this particular point, I'm subtracting them up. So what I'm left with, I'm left with this number 5. This is nothing but 5 mod 5. This is also 0. Okay, so this is also a subarray. So in the question that we have just seen on CodeChef, what you need to do is, you do not need to find subsets in exponential time. We have already proved such a subarray will always exist because of pigeonhole principle, because there can be two cases. If one of the numbers, if one of the sums turns out to be 0, that means starting from the 0th index till that particular index, you got the subarray. But if one of the number is not 0, then you have 5 numbers here and you have only 4 buckets left. That number would always lie in the range 1 to 4. Okay, or if you have n numbers here, then you will have n minus 1 buckets. So at least one number would repeat, and the indices corresponding to those two repetitions would give you the subarray. Okay, so that's how we have used the pigeonhole principle to prove this claim and solve this problem. Now this cumulative sum can be done in linear time, and you can maintain a kind of a frequency array, and you can check the place where the frequency is at least 2, that will solve your problem. Okay, so that's all for this video. Thank you. Hi everyone, in this lecture we are going to solve this problem. The problem name is gray similar code, and it is again a question from CodeChef. So it is given, we are given n 64-bit integers, and such that two consecutive numbers differ exactly at 1 bit. Okay, so let's say if the ith number is, let's say if the ai is like 11001, then ai plus 1 will only have 1 bit different. Okay, maybe this bit is different. Okay, rest all the bits are same. So we have to find 4 integers. Okay, so this is a small mistake. We have to find 4 integers such that their XOR is equal to 0, and we have to output yes or no if such 4 integers are possible or not. Now again, this is a problem from CodeChef, so let us look at the exact constraints. Okay, and the question is same, like you're given n non-negative integers, and AI is of the range 2 power 64. That means the number can be stored in long, and you need to check whether there are four numbers such that the following property is satisfied. Okay, so it is saying the XOR of the numbers, let's say the four numbers are A B C D, so A XOR B XOR C XOR D, this is equal to 0. This is the property that needs to be satisfied for this particular problem, and in the output we just need to print yes or no. So let us look at the value of n. So n, you can see it is a large number. N is of the order 10 power 5. And now what is the brute force approach? Okay, the let's talk about the brute force approach of doing this. So we are also given a sample input, so we have 5 integers, and the answer for this is yes. So there exist four numbers from this set, so that their XOR is equal to 0. Now let us look at one thing. So let us discuss what are the various approaches to solve this problem. So the first way is a brute force approach, in which what you are going to do, you're going to pick four numbers. Okay, and how do you pick four numbers out of n numbers? Simply by using for loops, and you would have nc4 options, and this would take order of n4 time, and since n is of the order 10 power 5, this solution will give you the time limit exceeded error. Okay, so the brute force solution will not work. The brute force will work for smaller values of n. Okay, for smaller values of n, let's say for n less than equal to 100, the brute force will work, because doing n 10 power 4 would be of the order 10 power 8. Okay, so now let's see what optimizations we can add to our solution. Okay, how do we optimize our solution? So the thing is, what we want is, we are not exploiting the property. So there is one information given in the question, that two consecutive numbers differ only at one bit, differ only at one bit. And another information given is the numbers are 64-bit numbers. This is also given. So till now in the brute force solution we have not used this information. Now we need to see what is special thing about this information and how we can use it. Okay, so two consecutive numbers differ at only one bit. So if I do a XOR of a number along with the next number, some ith number, okay, since they differ at only one bit, let's say this is the number, and let's say this is the next number. So if I do a XOR of both, what I will get? I'll get all zeros except one at one position. Okay, so it will be all zeros, but we will get one at one position. Okay, at any one position where the bits are different, I will get a bit 1. Now suppose I have lot of numbers. Okay, so I have numbers from a1 a2 up to let's say a129 a130 up to an. Okay, so what I am saying is, if I have at least 130 numbers, okay, if I have at least 130 numbers, if the value of n is greater than 130, I can say my answer would be always yes. I will tell you why. But if n is less than or equal to 130, okay, if n is greater than or equal to 130, the answer is always going to be yes. Let me just tell you why. So if you have 130 numbers, and if you do a pairwise XOR of all the numbers, okay, so if you do a XOR of these, a XOR of next two, your XOR of next two, XOR of next two, okay, so what is going to happen? You're going to get 65 pairs. Okay, you're going to get 65 pairs, and in each pair you will have a number of the form one of the positions will be 1. Okay, so only one bit would be set, only one bit would be set. Okay, because of the property that we have just seen, that if we do a XOR of two consecutive numbers, we get a number in which only one bit would be set. Now this one bit can occupy a position in the range 0 to 63. Okay, so that can be indexed from 0 to index 63. Okay, but how many pairs we have? Okay, so basically we only have 64 positions. Okay, we only have 64 positions. Okay, and but we have 65 answers. Okay, so we get 65 pairs, and each pair is of this particular form in which one of the bits is in this range. Okay, that means at least two pairs will have same value. At least two pairs will have same value. Let us assume the value is this much. That means if one of the pairs has a bit at, let's say, some kth position, there must be one more pair which has bit at the same position. So at least two pairs will have the same value, because all the pairs of the form in which all the positions contain a 0 except one position contains 1. Okay, and since there are only 64 positions for 1 but we have 65 such pairs, that means two pairs will have same value. That means the set bit at same position, set bit at same position. So now what we can conclude from here is, we can say, if we know, okay, there must be at least two pairs which are having the same value. Let's say the numbers a and b formed the pair p1, the numbers c and d formed the pair p2, and hence doing XOR of these two pairs p1 and p2, they will always produce the XOR 0. Let's say pair is p1, this pair is p2, p1 XOR p2 would be 0. So this would be always be yes if we can get at least 65 pairs. That means if the number of numbers is greater than equal to 130 in the array, the answer would be always yes. So this solves for the case when n is greater than or equal to 130. Okay, now let's come to the second case. What if n is less than if the value of n is less than 130? Okay, so if n is less than 130, then what we can do, we can say our brute force solution will work for smaller values of n. We can still optimize the brute force solution little bit. Let's see how we can do it. Okay, so let me just summarize. So if n is greater than equal to 130, we can say the answer is always yes, because we have proved by using pigeonhole principle that if we get 65 pairs and we have only 64 bit positions which are possible, then two pairs will have the same value, and doing a XOR of those pairs would produce an output 0. Okay, two pairs will have same value, and we can say that p1 or p2 would be 0. And let's say this pair is made up of a and b, this pair is made up of c and d, and doing a XOR of these would give me an answer 0. But if n is less than 130, okay, if n is not greater than 130, then what we need is, we can actually use a brute force approach. So we need to find out four numbers, a's or b's or c's or d, this is equal to 0. Or what we can do is, we need to find out a number d. So we can use three loops to iterate over the values of a, b and c, and we can say a's or b's or c must be equal to d. Okay, if this XOR is equal to 0, then if we find out if we just use three loops to iterate on all positions of a, b and c, so we can actually look for d. We can look for d in the array. Now how we can look for d? So there are two options. One option is you do the sorting and then you do the binary search. Okay, binary search for d. Another option could be if you can do hashing as well. Okay, if you hash, you can simply look for the value of d in just constant time. So that means this operation can be either reduced to log n operation, or if you do binary search, or it can be reduced to order 1 operation if you use hashing. Okay, so now the brute force solution can be solved in order of n cube time or order of n cube log n time, and since the value of n is only of the order 100, and this would take 10 power 6 operations, and hence this will get accepted. Okay, so you basically make a if else. If n is greater than equal to 130, output yes. If it is no, then use a brute force technique to check whether these 4 numbers are possible or not. Okay, that's what you are going to do. So that's all for this lecture. I hope you understood the solution, and that's it. Hi, so in this lecture we are going to solve this problem holiday. It's actually a pretty big problem statement, so I have written the summary here. The actual question is on the platform Spot, and let us try to go through the problem statement and try to understand this question. So it says people have many ways to save money on accommodation when they are on vacation. Okay, one of these ways is to exchange house with other people. Okay, so instead of going to hotel, people want to exchange houses. So there is a group of n people who want to travel around the world. They live in different cities and they can travel to other people's city, okay, and use that house. Now they want to make a plan for a destination for each person. There are two rules to be satisfied. All the people should go to one of the other people's cities. So if there are multiple cities, okay, let's say this person P1, it will go to some other city. This person P2, it may go to some other city. This is person P3, it may go to some other city. This is person P4, it may go to some other city, so that all people are able to exchange the house. Two of them never go to same city because they're not willing to share a house. Okay, so that means in the final output there would be some kind of permutation among the people. They want to maximize sum of people's travel distance. Okay, the total traveling distance should be maximized. The travel distance is the distance between the city and the city he travels to. Okay, so the entire distance traveled from source to a particular destination, okay, that is known as the travel distance for a person P. And there are n cities and there are n minus 1 highways connected them. The travelers always choose the shortest path when traveling. Now this is something that we need to see. Okay, so effectively what it is given, there are n cities, okay, and there are n minus highways which are connecting them. So that basically means if you have 3 cities, then there are only 2 highways. Okay, that means it will be in the form of a tree, it will not be a graph. Okay, so that means, or it, you can say it is a graph without a cycle. Okay, it's a graph without a cycle, and that is also called as a tree. Okay, so the structure of the cities is in the form of a tree structure. So maybe there are more cities here, so on. So you can see if you have 1 2 3 4 5 6 7 cities, then there are only 6 edges. Okay, so anything that follows this kind of a structure, it is a graph without a cycle. Okay, if you add a edge like this, then it will violate this property that there are n minus 1 highways. In this case you have n highways, so this edge should not be there. Now what is the meaning of the shortest possible path? Okay, the another condition that is given to us is they always take the shortest possible path while traveling. And second thing is we have to maximize the total distance. Okay, maximize the total distance of travel. That effectively means if this person 0, if it wants to go to the node 2, it will take the direct route, it will not uh, go like this. Okay, so one possible way could be it is going to go like this from 0 till this particular node. This is the shortest node. Okay, it will not do something like this, that it first goes to the node 8, and then it comes back. Okay, this is not how you're going to maximize the path. You're going to take the shortest route, but the distance might be maximized if you choose a different node. Okay, if 0 travels from this node to maybe this node, in that case it is possible that it covers more distance. Okay, so this is how you need to maximize the total distance. Okay, and I hope you also understood what is the meaning of shortest possible path. So let us discuss the rest of the statement. And they want to maximize the total distance traveled. The travel distance is the distance between the city and distance it travels to. All right, and we have already seen. So given the highways information, it is your job to find out the maximum total travel distance of all people. That is what we need to find out. So in the input we are given the number of test cases. Okay, each test kit contains two integers n, the number of cities, followed by n minus 1 lines, which denote the city x, the city y, and the length of the highway. So these are basically nodes and the edges. Okay, and here we are given how many cities we have in this particular test case, and this is the number of test cases. All right, so let us look at the input example 1. So in the input example 1, what we have 4 cities. Let's call them as city 1, city 2, city 3, and city 4. If you look carefully now, from city 1 to 2 there is a edge that contains a distance of what? It contains a distance 3. So this edge is of distance 3. Then there is also an edge between the nodes 2 and 3. This is of distance 2. There is also an edge between 3 and 4, which is also of distance 2. So this is 2, this is 2. And now we need to see what is the maximum possible distance that all the travelers can travel. So one way is if we just exchange these two. If I exchange 1 and 2, okay, the person 1 goes here, the person 2 goes here, the person 3 goes here, the person 4 goes here. So in this case the total distance traveled would be 3 plus 3 for 1 and 2 plus 2 plus 2, that is how much? 3 and 3 is 6, and 4, this is 10 units. Okay, but the answer is 18 because this is not the best way of arranging. Not This is not the way that will maximize the total travel. Okay, so let us look at another way. So yeah, this is 3, this is 2, and this is 2. So another way could be, let us exchange 1 with 4 and let us exchange 2 with 3. That means this person comes here and this person comes here, this person comes here, and this person goes here. So what would be the total distance traveled by person 1? It would be 3 plus 2 plus 2, and similar distance would be traveled by 4, so we can do twice of it. Between 2 and 3, 2 will travel distance 2 and 3 will also travel distance 2. So this is 4, this is how much? This is 14. So 14 plus 4 is what? This is 18. So you can see in this case the answer is 18. Okay, another possible way could be we exchange 1 with 3. Okay, 1 comes to 3's location and 2 goes to 4's location. So in this case the total distance travel would be twice of 1 goes to 3, so it is 3 plus 2, that is 5, that is 10. 2 goes to 4, which is like this, twice of 4. This is also fine. This distance is also 10 plus 8, 18. So there can be multiple possible combinations which are leading to the same output, but we are interested in the final output instead of finding out the combination. We need to find out the final output. Okay, so now let us see how we can approach this particular problem. Okay, so let's discuss an approach that will help us to solve this particular question. Okay, So one thing is clear, the value of n is large. Okay, we cannot find out all possible permutations of nodes and then try to find out the distance. Okay, the graph may be a complex graph. Okay, we don't know. Okay, so now one thing we know is that the total distance, okay, the total distance traveled would be nothing but, it would be, let's say, if the edges are like this, if the edges are, if the edges are e1, e2, e3, e4, and so on, okay, then the total distance would be nothing but some constant c1, okay, n1 times e1 plus n2 times e2 plus n3 times e3 and so on. Okay, so total distance would be nothing but, it would be weighted sum of edges. This everyone agrees. And what we need to figure out is, we already know the edge lengths. Okay, we know e1, e2, e3, that is given in the input. What we don't know is how many times each edge would be used. Okay, we need to find out what are the values of n1, n2, n3, and these values should be such that they follow the constraints and they should be able to maximize. Okay, so these n1, n2, n3 should be equal to the maximum number of people that will travel through that edge, so if we are able to find out what is the maximum number of people that will travel through that edge, we can easily find our answer by taking this weighted sum. Okay, now the question is, how do we find out how many people are going to travel through a particular edge? Okay, now let me try to figure this thing out, how we are going to do it. Let us talk about a particular edge. Let's say this edge is e3. I want to find out what should be the value of n3. That means how many people will actually travel through this edge. Okay, and we want to maximize that. So this edge breaks our graph or the tree into two parts. So one part is clearly visible. Okay, so one part is this one. Let me just mark it in green. So this is one part of the graph. Okay, let me write as part 1 and let me write it as part 2. Okay, let me write it as part 2. So now if you look carefully, what is going to happen? What do you think, how many people will travel through this particular edge? How many people will travel through this particular edge? So effectively we have 5 persons in this part, a b c d e f. So we have 6 persons here. Okay, we have 6 persons in this graph, in this part, and we have 3 persons in this part. Okay, maybe some ghi. Now what is going to happen? Okay, so I want maximum people should travel. So if I want to maximize the use of this edge, so I would be sending maximum people from part 1 to part 2, and I will be sending maximum people from part 2 to part 1. Okay, if I want to maximize the use of every edge. So now one thing is very clear, that if I try to send all 6 people to part 2, okay, can I send 6 people to part 2 from part 1? The answer is no, because part 2 has only three cities available. Okay, there are only 3 rooms or 3 cities available where that can accommodate at most 3 people. Okay, so I cannot send 6 people in part 2, I cannot send 4 people in part 2, but I can send 3 people in part 2. Okay, that means, and similarly, since 3 people are coming here, I can send 3 people from here as well. Okay, so what is the number of people that would be traveling through this particular edge? Okay, some ith edge, that would be nothing but minimum of persons in part 1, okay, and part 2, and twice of it. So it is nothing but 2 into minimum of this is what, this is 6, this is 3, and this is nothing but 2 into 3. Effectively, in the best case or in the maximum case, there would be 6 people who would be using this edge to travel from one part of the graph to another part. So if you do this thing for all edges, then you will get these coefficients and you can easily find out the weighted sum. Okay, so if this weight is, let's say, 4, then this edge would be contributing 6 into 24, that is 24 into our answer. Okay, we will add 24 to your answer. Okay, so I hope this part is clear, and this is what, where we have used the pigeonhole principle. Okay, so effectively on the right we have 3 holes, but we have 6 pigeons, so only 3 pigeons can travel to these 3 holes. Okay, and three pigeons from here will travel to these 3 holes. Okay, so it does not matter where they are traveling to, the only thing that matters is how many times they would be using this edge. Okay, how many times this edge is being used, and we will do it for all the edges, and this will effectively help us find out the total answer. Okay, so I will call this approach as a greedy approach. We are kind of finding the local maxima. Okay, and so we are finding multiple local maximas and adding the answer for all the edges. Okay, so if you want me to dry run on the given example, we can do it. So let's say this is A, this is B, this is C, and this is D. Okay, now along with this dry run, I would be discussing the implementation aspect as well, how we can implement it. Okay, so one way is you break the graph around every edge, and then you say, okay, I will do a DFS on this part. Okay, so if you do a DFS on this part and you do a DFS on this part, let's say you get the size of the first part as 1, the size of the second part as 3, and then you say, okay, this edge length is 3, so I will say minimum of 1 and 3 multiplied with 2 multiplied with 3. Okay, this is the weight of the edge. This is because twice the number of people will travel, twice of the minimum, and this is the minima. Okay, so this minima is kind of coming from pigeonhole. So we can say it is, this edge is going to contribute how much? It's going to contribute 1 into 2 into 3, that means 6 units. Okay, but what is going to happen for the other edge, that we also need to figure it out. So what we are going to do is, so this we know that this edge will contribute 6 units. So let us talk about the complexity of this approach. So we are doing DFS that takes order of v plus e time, and we are doing it for every edge, so multiplied with e. So it again ends up e square plus ev. So it may not pass all the test cases. So let me discuss a slightly efficient implementation of doing DFS. So what we are going to do, we are going to traverse this graph edge by edge. Okay, so let's say we start from this edge. This is having a weight of 3, this is having a weight of 2, this is having weight of 2. Suppose you traverse this edge, A makes a call on B, and you ask B, okay, give me the size of the subtree that is below you. So B will again run a DFS on it. It will make a call on C, and C will again run a DFS on its child. It will run a DFS on D. So once we run DFS on D, D does not have any neighbors that are not visited. D will return, okay, my size is 1. Okay, this edge is visited. So once this edge is visited, what we can do, we will start building our answer from this edge. Okay, because we are coming back. Now what we know is, we have a node C and it has a child D. So D tells its parent, okay, I have only one person inside this entire subtree. So that means how many nodes you have in the rest of the tree. Okay, how many nodes you have in the rest of the tree, that is nothing but, if one node is here, the rest of the tree will have n minus 1 nodes. And what is the minimum of these two? That is nothing but 1. Okay, so minimum of 1 and 4 minus 1, that is 3, into 2 into the weight of this edge, that is how much. So this this edge is going to contribute 4 units to the answer. Okay, all right. So now from C we are going to go back, and we are saying okay, C is also one node. So C is going to tell its parent that I actually have two nodes here. Okay, and if you have two nodes in this subtree, the remaining subtree is also going to have, okay, just lost the diagram. So we just lost the diagram. So let us recap what we were doing. So we said we will try to break between this edge. So we will figure out how many people will travel through this edge. So it would be minimum of, on the left side there is one person, on the right side there are three persons, twice of it multiplied with the weight of edge. So it would be 2 into 1 into 3, that is 6. We said we will try to break it for this edge. Okay, then there are two persons in this part, there are two persons in this part, it would be twice into minimum of 2 into 2 multiplied with the edge weight, that is 2. So it would be 2 into 2, 4 into 2, 8 units. And if we try to break about this edge, so there is one node here and there are three nodes here, it would be 2 into minimum of 1 and 3 multiplied with what, 2. So it would be again 2 into 2, 4. So this is 12 plus 6, that is 18. So you can see we are still getting the right answer, 18. But now the question is how we can do the DFS that we were discussing. So effectively, what happened in DFS is, let me just pick a different marker. So what happened is A made a call on B, okay, B made a call on C made a call on D, and D does not have any parent. D tells C, okay, I am a single node. So we get to know one of the values is 1. Okay, so from this node we get to know if you're talking about this edge, then what happens. So this child basically returns a value 1 because it is returning the size of the subtree. So it becomes 1 followed by n minus 1. So n minus 1 is, n is what, 4. 4 minus 1 is 3. So we get to know this value and we multiply it with 2, and we also know the edge weight is 2. So we get to know this answer, that is 4. So at C, this is the subtree, and C says, okay, whatever is the size of the child tree, I will add 1 to it, I will return to my parent. So C returns 2 to the parent. So it becomes 2 into minimum of 2 n minus 2. Okay, what is the size of this subtree? That is nothing but n minus 2, that is 2, multiplied with the edge weight, that is 2. So it becomes 2 into 2 into 2, that is 8. So we effectively get the answer for this row. So now at 3 we get to know the size of the subtree is what, it is 2. We add 1 to it, it becomes 2 into minimum of 3 comma n minus 3, that is 1 into 3. So this edge is now 3. So it becomes 2 into 3, that is 6. So we again get this one and we say, okay, this sum is what, this sum is nothing but 18. So effectively what we are doing is we are doing a depth first search, and from every child node we are returning the size of the subtree. Okay, suppose you have a complex tree like this. In this case, if you make a call here, okay, if you make a call here, it will automatically make a call here, here, and this subtree will return a size 3 to its parent. Okay, and we want to see how many times this edge is being used. So we'll find out the minimum of 3 and how many nodes are there in the other part of the tree, that is nothing but n minus 3. Okay, we are not using DFS to find out the other part because we know the total nodes. If 3 are in one part, the other part is going to contain n minus 3, and we are taking this minimum because we cannot fit a larger number of people into a smaller number of cities. Okay, so that's why we are taking minimum, and that's nothing but an application of Pigeonhole. Okay, so I hope now you understood. So what we have to do is we have to just do a DFS in a single pass, and while doing DFS we have to keep a track of these values, and this will take overall complexity of order of b plus c, that is linear in time. Okay, so that's all for this lecture, and thank you. Hi, so let us discuss the implementation of holiday accommodation problem, and we'll write the code for the same. So first of all, we'll write the code for main. So in the problem we have multiple test cases, so we have to take input how many test cases we have, and for each test case we need to input the total number of nodes and the list of edges. Okay, so there is a edge from u to v with a weight w, and we need to create a graph. Okay, so for graph we'll create a adjacency list, and it is a weighted graph, so I will need a pair to store it. Okay, to store each edge. So I'll just tell you what we are doing. I need vector, and I also need, that's it. Okay, I need vector. Now what we are doing is we are taking input an edge. Okay, there is an edge from u to v whose weight is w. We are storing it in the form of a, so this is nothing but an array of vectors. Okay, it's a array of vector. So we have each element of the array which is a vector. Okay, so if I say this is node u is 1, so then it is connected with, let's say, node v, it is connected with node v2, it is connected with node v3. So I'll store the neighbors here, that v1 has weight w1, v2 has weight w2, v3 has weight w3. So that's why I need a vector of pair, and this we have as an array of size 10 power 5, because that's the constraint given in the problem. Okay, so if you see here, n is of the order 10 power 5. That's why we need to create this vector. Okay, and so what we are going to do, we are going to say, okay, let's say we are at the first test case. So while test case is less than equal to total test cases, I can say tc equal to tc plus 1. So here we are going to do the work for each test case. So we'll take input the number of nodes for that graph, and for every test case we need to reset the adjacency list that we are creating. So we can say for int I equal to 1, I less than equal to n, I plus plus, I can say adjacency of I dot clear. So now why I'm doing from 1 not from 0, because the numbering of the nodes in the problem, this numbering is 1 based, it is not 0 based. Okay, so that's why we are just not using the 0th vector, we are starting from the first vector. So reset the adjacency list before every test case, because the graph is different. Okay, before every test case. All right, so after that we need to scan the graph. We'll take input n minus 1 edges. So for int I equal to 1, I less than equal to n minus 1. So we'll scan a edge. We'll say, okay, scene u, v and w. So if there is an edge from u to v, we'll say, okay, just scan it. And in order to construct that edge in the memory, what we need is, we'll say, okay, in the adjacency list of u, we'll push back a pair of v and w, and in the adjacency list of v, we'll push back a pair of u comma w. Okay, that's how we push. So adjacency list of u dot push back a pair of v comma w, and adjacency list of v dot push back u comma w. So we are done, and now what we need to do, we need to do DFS to calculate our answer. So I can say long answer that is equal to 0. Okay, and now we need to write a DFS function that will work on this graph, and that will compute the answer for us. Okay, and once the answer is there, we can print it. So now the way we are going to define this DFS function is, it's actually not going to return us the answer, but it is going to give us the size of the tree. Okay, so this DFS will give us the size of the tree from the node where it is called. But we'll do two things. We'll take the current node, let's say we are at u, we'll take what is the parent node. We will soon see why this is needed. we will need the adjacency list. So I can say vector of pair of int, okay, and we need this adjacency list array with us, and we need the answer variable, and we need the number of nodes. Okay, so here we are passing this array. So array by default is passed by reference. Okay, so we don't need to yeah, so we are passing this array, and this array is passed by reference. Okay, so what is this answer? So this is the final answer that we need to compute. We are accepting an answer by reference, and we are going to update this answer. Okay, so maybe I can do hash define ll as long, and here I can do ll answer. That is also fine. And this n is the total number of nodes in the tree. So now what we are going to do, let's say we are going to DFS on a tree. Okay, we starting from node 1, and let's say there are so many other nodes, let's say 3 4 5 and maybe 2 6 7 so on. Okay, let's say there are so many nodes. We start from this node, and what we are going to do, we are going to say, okay, let's go and traverse the entire tree. So first, let's say we traverse this edge. Okay, so what we are going to do, we are going to say, okay, let us assume the current size of the tree, the current tree size is nothing but 1, and then we will iterate over all the neighbors of this node. So for every pair that is present in adjacency list of u, what we are going to do, so if you look at 1, so 1 would have neighbors as what, it would have 6 and its weight, it would have 3 and its weight. That's it. 1 has only 2 neighbors in this case. So what we are going to do, we are going to say, okay, the node v is nothing but p dot first, and the weight is nothing but p dot second. So effectively in the adjacency list we are storing two things, w1 and w2 as well. This is p dot first and this is p dot second. What we are going to do, we are going to say, okay, we are going to make a call on these child nodes. So I can say int child tree size is nothing but DFS of that node. So that node is v. The parent of that node is nothing but the current node, which is u. So the parent value would be u. The adjacency list will remain as it is. The answer will remain as it is. The number of nodes will remain as it is. Okay, so we make a DFS call. Now this node is going to tell, okay, it will again do recursively some work, and it will return, okay, my size is 3. So this child tree size would be now 3. And what we are going to do, we now know that this child tree size is 3. So we'll count the contribution of this particular edge in the final answer. Okay, so edge contribution, that means what is the contribution of this edge in the final answer. So that would be nothing but 2 into minimum of child tree size. What is the number of nodes in the other part of the tree? In this part, this is nothing but n minus child tree size. Okay, into the weight of this edge, that is nothing but wt. So what we can do is we can add this to our answer. So edge answer plus this edge contribution. And another thing we need to do is, since 1 has already called on this part of the tree, so the size of 1 would increment by this value 1 plus 3. Now 1 would make a call on this part of the tree when we want to compute the contribution of this edge. Okay, because we are iterating inside this for loop. Now we come to this edge, that is 1 comma 3. So for that, it will again make a call. It will say, okay, my edge contribution is 3, so it will become 1 plus 3 plus 3, that is 7. Okay, but that will happen in the next iteration. So I can say also update the tree size by adding child tree size. So I can say current tree size plus equals child tree size. Okay, so once you have done with all the neighbors, what you can return is, you can return the current tree size. Okay, return current tree size. So this one will actually return 7 in the main, which again is not very useful for us. But what do we need is, so now there is one case that is left that we have not handled is, now suppose you have again this kind of a tree. Okay, let's say 1 2 3 4, and you come here, and in the neighbors of 2 you have 3 and 4. Okay, in the neighbors of 3 you only have one node, that is 2. So at 2, when you make a call on 3, 3 will make a call on its neighbors, so 3 will see 2 as its neighbor. Okay, so what we are doing is, since no cycle is present, okay, so we are not maintaining a visited array. So either you maintain a visited array to make sure you do not visit a node twice, but in this case what is going to happen, when you come from 2 to 3 and you look at the neighbors of 3, you say, okay, I'll make a call to 2. So that will actually give you a segmentation fault, okay, because of kind of an infinite recursion. You're going to 3 via 2 and you're going to 2 via 3. So you will be stuck inside a loop. Okay, so what you need to do is, if the neighbor of a node is the parent, okay, like the neighbor of 3 is the parent 2, you don't do any work in that case. Okay, so for example, 1 2 3, so from 1 you come to 2, from 2 you come to 3, from 3 you go to 2, or like from 2 you go to 1. So you 2 also has a neighbor 1. Okay, 1 also has a neighbor 2, 3 also has a neighbor 2, and 2 also has a neighbor 3. Okay, so what you need to do is, from any node you don't need to make a recursive DFS call on its parent. Okay, so you can check if the value of v is equal to the parent of current node, you will skip that node, you will say continue. Okay, so this will actually serve the purpose of having a visited array. We don't maintain a visited array explicitly, since the graph does not contain a cycle, so we use handle for cyclic case. Okay, kind of. Okay, or skip the parent node which is acting as a neighbor in this case. Okay, so this will avoid the work for us. And now what we can do is, we can say, okay, let's make a DFS call, and in this DFS call what we are going to do, we are going to pass in the parameters. Okay, the starting node is 1, the parent of starting node you can put any value, let's put -1, the adjacency list, and the answer, and the value of n. Okay, that's what you need to do, and you need to print the output for every test case. So I say, okay, let's see out the test case number and the answer. So we need to give some inputs to test our code. So I'll just copy the input from Spoj. Okay, and we should get 18 and 62 for this input. Let's run the code. Okay, so we are getting 18 and 52. Okay, did we miss something? Let me see if I missed something. Okay, so what I missed was just this last line of input. If I run my code again, you see we are getting the correct answer, and I just submitted on Spoj also. I got a correct answer there as well. Okay, so I hope you really understood this one, and what we have done is exactly same what we discussed in the algorithm. Okay, so what we are doing for this node, let's say we have this tree 1 2 3 and 4. We start doing DFS from this node. We say, okay, what is the tree size? So 2 tells, okay, this size is 3, but 2 first makes a call on 3, 3 makes a call on 4. At 4 what we have, we say, okay, this current tree size is 1, and what is the neighbor of 4? There is only one neighbor of 4, that is 3. In that case we continue the for loop, and it does not run for any iteration, so we return the current tree size, that is 1. So 4 effectively returns 1. So then we contribute the contribution of this edge when 3 made a call on 4. Okay, so during this iteration only, so when 3 made a call on 4, what happened is, we computed, okay, this will be used 2 into minimum of child size, that is 1, and other option is 4 minus 1, that is 3, into the edge weight, that is 2. So it is 4. Okay, this contribution is 4, and 3 says, okay, my size is 1 plus my child size, that is also 1. So 3 will return 2 to its parent. Okay, so this contribution would be nothing but 2 into minimum of 2, that is 2, into 2, so that is nothing but 8. So this contribution comes out to be 4. So this 2 returns 1 plus child size, that is 3, 2, 1. So this edge is used how many times? So it says 2 into minimum of 3 and n minus 3, that is 1, into the weight of this edge, that is 3. So it is used for 6. So 4 plus 8 plus 6, that is the sum that we add in the answer every time. And to the main we return an answer 4, but in this answer we have 6 that we print here. Okay, so that's the answer we are printing here. So I hope you understood this problem, and that's all.